Penultimate presentation is John Yeow. And give a second to load this, I guess. On here? Oh, good, it's on here. Okay, John will be talking about the systems, from systems design engineering, imaging with nano micro devices.
Thank you, Dominic. My name is John Yeow. I belong to Systems Design Engineering. I have a lab called the Advanced Micro Nano Devices Lab. If I'm going to talk about a subset of the project that we're currently involved in, but if you're really interested in details of what we do, I have the website that's listed on there. So you're certainly welcome to go to the website to see the kind of project that we're currently involved in. Currently, my group is working on anything that has to do with any micro nano system. A lot of what we do has to do with biomedical applications. So today I pick a small subset of the project which has to do with imaging project applications. So the first project that I'm going to talk about is currently we are working with Princess Margaret Hospital to miniaturize an endoscope. The other speaker has already talked about OCT, so it will be a lot easier to talk about why we want to do this. The imaging modality we're using is also OCT. So now if you can imagine the imaging optical light that we use to image tissue is coupled into a fiber optic, and the fiber optic is traversed through the entire endoscope, and the endoscope is going through, say, the esophagus or the other way around. So we want to miniaturize that because that's a painful process. So usually people are really appreciative of what we do. Because of the conventional technology that's right at the tip of the endoscope, that does not allow us to miniaturize the endoscope. So we went to a MEMS technology. So MEMS stands for microelectromechanical systems, and the advantages of using MEMS is listed up there. One thing that I would like to mention is currently if we want to perform an OCT imaging within the colon, it's usually a line scan, which means that the mirror would rotate in 360-degree format. We would actually direct the light beam at 360 degrees to perform a line scan. So the problem with that is usually physicians are only interested in a small portion of tissue. So 90% of the time we are directing photons to the wrong places. So the other thing is we want to achieve a 2D scan. So we want to achieve an area scan rather than a line scan. So the next slide, you'll see the micro mirror or the MEMS mirror that we have fabricated to be integrated at the tip of the endoscope. Right now, we have a second project with Sandy Brook Hospital, not integrating within the endoscope, but integrating it within the catheter, so we can insert into artery for imaging and stuff like that. So for this particular mirror, we have fabricated this back in 2002. The dimension you're looking at the center square portion is actually the reflective surface of the mirror. It's 1,000 micron by 1,000 micron. The entire scanner structure is 1,700 micron by 1,400 microns. So in the world of MEMS, they're really gigantic mirrors. But what's the technical challenge of making such a big mirror that's suspended by really thin torsion bars? And the reason we want really thin torsion bars is because we want to minimize the driving voltage, because we're driving this mirror using electrostatic forces. So imagine it's 1,700 micron by 1,400 micron. They're suspended by two pairs of torsion bars, but the outer torsion bars has a length. You have a close-up picture of that. It has a length of around 200 micron, 200 micron in length, 6 micron in width, and only 1 micron in thickness. So to put that into perspective, it's almost like suspending the entire soccer field on two planks, of which the smallest dimension is only 8 centimeters. So we have successfully released and fabricated that, and we have integrated that to do some imaging work at St. Michael's Hospital. And I want to respond to what Dita just said. There's nothing wrong with imaging a fruit fly. So the first thing. The third thing we did was we tried to image the fruit fly, And the MEMS mirror it's because it's suspended by two pairs of torsion bars, so it has capability of XY scan. So we can actually achieve an area scan. So in OCT, obviously, can go into the axial direction, so we can image within the fruit flies. So this image was acquired back in 2003. What you're looking at here is the central nervous system of a fruit fly in 3D. So you can actually see on the top portion, the wings of the fruit flies are clearly visible, and the nerve ending of the fruit fly goes on both sides. So it's fairly good-looking fruit flies. It's very symmetrical. So that's an ongoing project. We are still working with Princeton Market Hospital so that will be a next generation of this. The other project, we're currently involved, and we're working with two groups. We're working with a group in Princeton Market Hospital in terms of making radiation oncology devices. And the other project is with Dr. Rob Barnett, and we'll talk about that later. That's about detecting of X-rays. So really what we want to do, this has to do with the, I don't know if this is going to work, but. Here is the IMRT, which stands for intensity modulated radiation therapy. As you have collimators which move along, and that could actually block or let radiation beam through, and we can actually control the intensity of that. So I'm running out of time. So the project with Princess Margaret Hospital is we're trying to make an X-ray machine. We want to make a portable X-ray machine. In the last slide, you'll see the X-ray machine is actually quite big. We want to miniaturize that. And we do that by using nanotechnology. And this is sort of a preliminary experiment that we have performed at Waterloo. That's last year. And it shows very, very promising results. I won't go into detail. And the other project is with Rob, and since we know that the profile of the radiation beam is not going to be constant, we're working with Grand River Hospital in terms of making nanotechnology-based radiation sensors, so dosimeters, so we can actually profile radiation beam as it moves across a patient. So that would conclude my talk, and these are the collaborators and funders of my lab. Thank you. Yes, it's a single mirror which has the capability of alpha and beta rotation, so we can actually create.
You scan it around and reflect opposite parts.
That's right. Yes.
And when you enter the fruit fly, is that mirror inside the fruit fly?
No, it's not. We wish we could do that. So the fruit fly is actually sitting on an optical bench, so we actually clamp it down and then freeze it, and then hopefully it doesn't move. And so, yes. Yes, that's right. We still gonna have the catheter. Remote control. Oh, okay, yeah, that's right. Because at this point we are looking at OCT because we need some way to deliver the optical beam right to the tip of the catheter. So what you're talking about, it's probably like a endoscopic capsule with say white light video, with video capability. Yes, certainly that's one way with wireless, but for this optical modality, we need a way to deliver light beam right to the tip of the endoscope or the catheter.
And the other quick one is that you mentioned you're using nanotechnology here. Which part is nanotechnology involved?
Okay, prime example is this X-ray machine. The conventional way of generating X-ray, it's if you can imagine a light bulb, a tungsten light bulb. You have metal filament on there. You heat the metal filament up to thousands of degrees of Celsius. Then spontaneously, electron will be emitted from the metal filament. So it's a matter of imparting kinetic energy to the electrons. So now you have really fast moving electron hitting a heavy metal to generate X-rays. So that's sort of an X-ray generation in the nutshell. So the problem with that is manifolds. One thing is we have to heat up the metal filament to really high temperature, so its power consumption is really high. Maintenance of that is really expensive because very much like a tungsten light bulb, it has a finite lifetime. And miniaturization of that is obviously it's almost impossible to do. So using a carbon nanotubes, in this case what we're using is if we place a carbon nanotube between, say, two plates, a capacitor, it will spontaneously emit electrons. So each strand of carbon nanotube would essentially act as electron guns. So now it's really, we have access to free-flowing electrons. So it's just really a matter of slapping an anode right at the other end such that the electrons. So in this case, is the nanotechnology part, we're using a nanomaterial to generate X-rays.
So I assume this technology was developed already somewhere.
That's right. Well, the leading group for the X-ray machine is Otto Zoll at the University of North Carolina. So at the University of North Carolina, Chapel Hill, what they have created was and they have in fact generated X-ray and in fact 3D tomography of images that they have created. But what we're looking at here, I have to admit that we are playing catch up to the group at the University of North Carolina. But we're looking at different focus with Princess Margaret Hospital.
John, you did a seminar. We'll have to cut the two questions, but you did a seminar recently, and I believe it was that went onto the web. Did it not?
I'm not too sure.
Not sure.
I might be.
Anyway, John did a seminar an hour length, and it shows the devices, including the X-ray system. So thank you very much.
Thank you.